AI-enabled manufacturers are currently capturing OEE gains of up to 15 percentage points using the assets they already own. For the 82% of ASEAN facilities still operating on fragmented foundations, this gap has become a survival risk, one that cannot be solved by simply rushing to deploy process-level AI agents, as these pilots are almost universally failing. The core problem is a structural misconception. Plant operators often treat artificial intelligence as a software application that can be bolted on to existing disconnected operational technology. The previous wave of Industry 4.0 focused on basic connectivity to see the floor. This new AI inflection point is different. It requires the infrastructure to think and decide in real time. Data from the World Economic Forum confirms that manufacturing AI pilots consistently stall at the proof of concept stage. When these pilots fail, the algorithm is rarely the problem. The failure stems directly from a digital infrastructure that is insufficient to support the AI layer. To accurately predict whether a facility can support AI, we look at the Smart Industry Readiness Index, or SIRI. Originally designed to measure basic digital maturity, SIRI now functions as a strict mathematical baseline for AI readiness. This 16-dimension grid maps the SIRI framework. To deploy AI successfully, a facility needs to score above a 3.0 threshold across specific technology subdimensions. Physically, a 3.0 means machine data flows continuously into a structured layer, and local servers can run inference models right on the factory floor. If a facility scores below a 2.0 in connectivity, it physically cannot feed real-time data to an AI model. Below a 2.0 in data analytics means there is no structured pipeline available for training. To reach that viable threshold, a facility must build a 5-layer stack, starting with reliable power at the bedrock, moving up through connectivity, a unified data namespace, edge analytics, and finally, the autonomous AI agents at the top. Understanding exactly how far your operation sits from that 3.0 mark is the only way to avoid funding a software pilot on a physical foundation that will inevitably collapse it. The absolute bedrock of that 5-layer stack is physical power quality. This power waveform graph illustrates why edge AI servers and industrial computers are uniquely vulnerable. They rely on micro fluctuations in voltage remaining strictly within tolerance. A voltage dip lasting just 80 milliseconds can corrupt a machine learning inference cycle, trigger a false equipment shutdown, and destabilize an entire production batch. To secure this layer, facilities use the SEMI F47 standard as their baseline for power stability. A semiconductor facility in Singapore achieved this compliance by deploying ProDisk technology across their critical tool circuits. By stabilizing their power foundation first, they successfully protected their deployment of an AI-driven visual quality inspection system. Artificial intelligence algorithms execute decisions in sub-millisecond cycles. This speed makes power quality a core system-level design requirement, as even micro-fluctuations can break the logic of a live inference engine. With the power stabilized, we move up to the second and third layers of the stack, connectivity and data analytics. Most production environments operate in a data desert. They generate thousands of operational events every minute, but the process values sit inside logic controllers and are never logged. An AI model cannot learn from data that evaporates. Even highly automated machinery becomes an obstacle if it operates as a disconnected island. AI requires the full operational context, recipe parameters, equipment state, and upstream quality to optimize yield. The engineering solution is to deploy communication protocols like OPC UA and MQTT to bridge these isolated nodes and continuously extract machine data. That raw telemetry must then be structured into a unified namespace, a single queryable database that provides the exact operational context an edge machine learning model needs to function. When a mid-sized electronics manufacturer executed this exact connectivity program, they deployed an edge anomaly detection model and achieved a 6.8 percentage point improvement in overall equipment effectiveness within 12 months. Autonomous AI agents cannot optimize a production process they cannot see. Structured, continuous data pipelines are the mandatory fuel for industrial intelligence. The same data infrastructure built for connectivity also enables a direct alignment between AI and energy sustainability, a high-margin commercial opportunity that most facilities overlook. By training an AI model on granular, sub-metered energy data, operators can identify micro-anomalies in power consumption long before physical degradation occurs. As an asset wears down, its energy signature changes. Capturing that subtle shift provides an automated, highly accurate early warning system for mechanical failure. The precise sub-metering infrastructure required for corporate ESG reporting simultaneously generates the exact dataset needed to run AI-optimized predictive maintenance and dynamic production rescheduling. The fourth layer of the stack protects the entire operation, the OT security imperative. Deploying AI inference engines directly onto industrial PCs at the edge vastly expands a facility's operational technology attack surface. If an attacker infiltrates a flat network, they can feed corrupted data directly into an AI model that controls process parameters. This inflicts severe yield damage without ever triggering traditional SCADA alarms. To prevent this, facilities follow the IEC 62443 standard, enforcing rigid network segmentation that isolates the IT systems, the operational technology, and the AI inference layers. A flat, unmonitored factory network blocks AI deployment entirely. On an automated floor, machine intelligence and network security are completely codependent. Even with perfect physical and digital infrastructure, a facility must address the final dimension of the SIRI assessment, the organization. Technology readiness fails without human literacy. An AI-resistant organization features operators who lack the specific training required to interpret, validate, and trust AI-generated recommendations. An edge computing system can generate highly accurate predictive maintenance work orders, but it delivers zero return on investment if middle management ignores the outputs. Building the organizational capability and governance frameworks to act on machine recommendations is as critical as writing the algorithms themselves. In previous manufacturing cycles, a late adopter could always catch up by purchasing new capital equipment. The economics of industrial AI do not work that way. This chart compares standard equipment upgrades against the compounding AI data moat. Because AI models continuously learn, a competitor with an 18-month lead in deployment possesses 18 months of exclusive failure pattern data that a late adopter simply cannot buy. Deferring a SIRI assessment and transformation roadmap means choosing to fall further behind at an accelerating rate. The actionable first step is to commission a SIRI assessment. This identifies exactly which power, connectivity, and security gaps must be closed before committing capital to a software application pilot. Manufacturing competitiveness now depends less on physical assets and more on the intelligence layered upon them. But that intelligence only functions on the physical and digital foundations established long before the first pilot begins.